when we studied minimum cost spanning trees, we saw two algorithms. The first one was Prim's algorithm, which, like Dijkstra's algorithm, tried to extend a tree by finding the shortest edge connected to the current tree, and the other was Kruskal's algorithm. So in Kruskal's algorithm, we built up a tree bottom up. We started with disconnected nodes and then we connected them by adding the shortest edge possible. So we begin by processing all the edges in ascending order of cost. So we sort the edges, you pick up the smallest edge, and each time we pick up an edge, we see if the edge forms a cycle. So we have a collection of components which have already been joined together by the edges, and if the new edge doesn't create a cycle within a component, we add it, and in the process what happens is that the endpoints of the edge u and v belonged earlier to different components, because if they were in the same component, the component is connected, it would form a cycle. But having now connected these two components together, we must merge the components as we go along so that we don't add another edge within this component. So the main difficulty that we saw with implementing Kruskal's algorithm efficiently was precisely this task of keeping track of where the components were at any given time. So we know that in the beginning it's all disjoint because it's a bottom-up algorithm, everything is a singleton. But as we go along and edges are added, which nodes are part of the same component, which ones are different components, this was the problem. So abstractly, what we have is a collection of vertices which are partitioned, right? So this is a collection of disjoint sets. Every vertex belongs to one of the partitions and no vertex belongs to two partitions. So the collection of partitions together gives us the full set, but each collection in that partition has an empty intersection with every other collection. Right? And now given this partition, so we have this kind of a picture that we have a set, right, and it has now been divided like this into these disjoint partitions, and now I say I give you a vertex u and I ask which partition it belongs to. So that is this expression, this function called find, right. So find tells us which partition a given vertex belongs to. And similarly, now when I take, say, u belongs to this and say v belongs to this, then after this edge has been added, so I have now found an edge which connects u and v, now these two become the same partition. So I have to have a second operation which says, given two elements of the set or the collection which I am dealing with, take their partitions and make them into a single partition, right. So the union operation and the find operation, and what we actually saw in Kruskal's algorithm was this union operation is what took us time, because we had to find all the other vertices which are in the same collection as u, same partition as u, and convert them to the same partition as v. So what we need is a data structure which can implement these operations. So essentially we have a set of elements which is partitioned into components. So as we said, partition means that C1 union C2 union Ck is actually all of S, and each element small s in S belongs to exactly one of the Ci's or Cj's. So this is what it means to be a partition, and now we need to first create the initial partition. So the initial partition is going to be the one where every element is on its own, right. So you have a singleton partition containing just S for every small s in your set, and then we have these two operations, as we said, find and union, right. So find tells us the name of the partition or the name of the component that S belongs to, and union, given two set elements S and S prime, gives us back a single component for all the elements in the same component as S and S prime together. So let's, for simplicity, assume that our elements are numbered 0 to n minus 1. This is what we typically do even for vertices when we deal with graphs, right. We typically use 0 to n minus 1 as the names of our vertex set. So we will set up a mechanism to keep track of the components, and the easiest way is to have either a list or an array or a dictionary, where now, because these are 0 to n minus 1, I can interpret these as indices in the list or as keys in the dictionary or as positions in the array. So if I look up the ith element of component, it will tell me which component the element I belongs to. So now what does make union find do? Make union find basically creates names for the components which are the same as the vertices. So I have elements 0 to n minus 1, and I also have components, Okay, so this is just for convenience. I don't want to create another set of names. So the components are also called 0 to n minus 1. So 0 goes to component 0, 1 goes to component 1 and so on, because I need a name for the set. Right? The component containing 7, the component containing 6. So I need a name for that set, and those names are going to be just the same 0 to n minus 1. So component of the element I will be the component I. Right? That's what this is saying. Component of the element I. So this is the element, right? And this is the component number. Right? So this is how we set up our thing and make with this make union find. So we have this say dictionary component, and now when I want to find out which component a vertex I belongs to or a set element I belongs to, I just query this dictionary. I probe it with the index or the key value I, and what is stored in the dictionary is the component number. So initially it's I, and it will change as it goes along because of unions. So let's see how union works. So union, as we saw, is basically a sequential scan, right? So you want to now take two elements I and j and combine their components. So over time they have reached some component name. So if I look at component of I, it is some C old and C new, because I am going to merge in this. I am assuming that I am going to put everything which is in component of I into the same component as j. So I am not going to change the names of the component for the same component as j. I am going to change the name of the component for things which belong to the component of I. So let's say the component of I is the old component C, and component of j is a new component C new. Now I have to take every vertex, and this is the part that is inefficient. I have no idea which other nodes have the same component as I. So I have to take every other vertex, and if that vertex has a component which is the same as I will reset its component to be the same as j. Right? So this is one linear scan which is proportional to the size of the set, which I have to do every time I do a union. It doesn't really matter whether the component of I was small or not. I have to look at every other vertex because I have no indirect information about which other vertices have been merged with I so far. So what is the component of I contain? So with this, it's easy to see that this make union find takes order n, because I have to go through and label the component number as I for every vertex I. So this is just a simple linear scan across all the elements in my set. Find just looks up a dictionary. So if we assume that it's a dictionary or an array with a constant time lookup of the ith element, then in constant time or O1 time, I will find the component for a given element I. But union, as we can see, takes time proportional to the size of the set, because I have to go through every element in the set and check if it has got to be merged or not. Right? So whether or not it has to be merged, I have to check it. So this is much like in an adjacency matrix representation of a graph. In order to find the neighbors of a vertex, you have to scan all the columns. Whether or not this vertex has few neighbors or has many neighbors, you have to scan all the columns to find the neighbors. So in the same sense, you have no idea how many elements share a component with I. So you have to scan all of them, and wherever you find something which shares a component with I, you have to move it to j. So this means that one union operation takes order n time. So if I give m union operations, then it's going to take m times n time, right? So this is going to be the bottleneck that we saw, because in Kruskal's algorithm, we have to add n edges or n minus 1 edges to make a spanning tree. So we do order n merges, right? And naively speaking, if we do order n merges and each merge takes order n time, then I spend order n squared time executing all of Kruskal's algorithm, and that's what we are trying to improve. So how do we improve this? Well, what is the bottleneck, right? The bottleneck is that we don't know. So if I am sitting here and if I have a component which contains I don't know what are the other vertices in this component, right? So this whole component has some name C. So I know that component of I is C, right? The question is, what other vertices have component C, right? So which are the other vertices in the same component? So now we keep track of a dictionary going the other way. So component tells us, given a vertex, which component it belongs to. Members tells us, given a component, which are the vertices which belong to it, right? So members of C will be a list. it will give me a list of vertices. In general, initially, for example, I will have members of the ith component will just be the list I, right? Because initially every component has only one vertex, but as it grows, it will be a longer list, right? And of course, now since this is a list, I can take its length, right? I can take the length of this members C, and I will know how many vertices belong to this component, but I don't want to actually spend time computing the length each time, so I will separately store this as size of C, right? So I am keeping track of two new dictionaries. One is members of C. Members of C says give me a component and give me the list of vertices belonging to this component. Size of C says how many vertices are there, which is just the length of that list, but I don't want to compute that list explicitly each time, so I'll just keep track of it because it's easy to update, as we will see. So now given this, let's see how to do our implementation, right? So first we have to implement this make union find initial step where we create these singletons. So we had this old step which we repeat, which is for every vertex or every element I set the component of I to be the actual component I itself. So remember that we are using I for both the 0 to n minus 1 to name both the elements and the components. So the component of I is just the component I. On the other hand, we have to now do the reverse map. So we have to say what does component of I contain? Well, members of I is the list containing I, and size of component I is 1, right? Because I have only singletons at all points. So this is the initialization, very straightforward. What about find? Well, find doesn't update anything. Find merely looks up the component. So it doesn't have to look at members or size because it just needs the information in the dictionary component. So as before, find of I just looks up component of I. Union is where we were having problems. So let's see if we can make union a little more efficient, right? So as before, we find out the names of the components of the two vertices or two elements we are dealing with, I and j. So we are going to, as before, assume that we are moving everything in the component of I to be in the component of j. So we call the component of I as C old and the component of j as C new. And this difference now is that instead of going over everything, before we were doing this for loop over every element in our set or every vertex in our set. So we are going from 0 to n minus 1. But now I don't have to do it for every vertex because I know which ones have to change. The ones that have to change are the ones that are in the same component as I. So I just have to look at the list members of C old, and for every k in members of C old, I will first of all change its component, right? I will update its component from C old to C new. But now I have to keep track of these other things as I go along. So I have to take this C new component and append this new element to its list. So a k is now being added as a new element in members of C new, right? So as I change the name of the component of k from C old to C new, I go to the members of C new and I add k to it. And when I add k to it, its size also changes. So I also increment the size of C new by 1, right? So these are two extra steps which happen when I relabel, when I move a vertex from this component to that component, I must add it to its list members and I must update the size by 1. So this is simple enough. Right? So the question is, what have we gained, right? Because what we have gained really is this step, right, compared to our earlier implementation, because this is still order n, right, and this is still order 1. So the question is, what have we gained in union, right? So the point is that by going over members of C old, we can get away with only working with this many elements rather than this many elements, right? So when I relabel, instead of looking at order n elements, I mean looking at order of the size of the component, right? So this is similar to our graph theoretic things where we say that when we look at the neighbors of a vertex, we are interested in the degree of the vertex, the actual edges rather than all the neighbors which are not named. So in the same spirit, we are only interested in those elements which belong to this component. We are not interested in scanning all the components, so we are explicitly keeping that in this members list. So the question is, okay, so this is fine, we are using members here, okay, but why are we keeping track of the size? Because there is no apparent reason in this whole thing except that we have to update it correctly and all that. Nowhere are we using size in this union operation, right? We are just updating it, right? We are updating it for sure, but we are not using the fact that the size is available to us. So the way we will use size is as follows. We will always choose whether to, so we remember we have a choice. We can either go from I to j or j to I. Which component gets relabeled as which component? Do I make everything in component of I point to j, or make everything in component of j point to I. So that is where size will play a role. So size will say that we always merge the smaller component into the bigger component, right. So we have basically two components. So if I belongs to C and j belongs to C prime, I have to decide whether to make everything in C the same as C prime or everything in C prime. So the final component that survives, is it going to be C or C prime? So the rule is that the larger component will survive. So if C is smaller than C prime, I will relabel everything inside C to be C prime, and if C prime happens to be smaller than C, I will do the opposite. So that is the crucial decision that size gives us. So a priori this does not seem to be so helpful. Remember, our problem was that when we were doing this as range of n, right, blindly, we were spending order n time on every merge. But now we are spending something proportional to the size of the smaller set. But the size of the smaller set could still be almost half, right? It could be half plus a little bit, half minus a little bit. So in the worst case, a single merge operation could still be order n, because it could be take n by 2 steps, right? So we have not really guaranteed that an individual merge operation is less expensive now up to an order constant factor. Of course, it will be half as expensive, but half is not good enough, right? It's only a constant factor. We want something which is a little more strong than half, right? So it turns out that this we cannot deny. I mean, it could be that an individual merge will cost half n time, but it will not happen frequently. So we have to do our accounting a little carefully. So we are not going to change the implementation. This is our final implementation, but we are going to argue that this is good enough when we have this rule, right, of always merging the smaller component to the larger component. We are actually going to get a sizable improvement. So why does this happen? Well, basically, if I take a vertex I and I track what happens to it, right. So initially its component is I. The first time it is forced to change its component, right, it changes its component from some C to C prime, then from C prime to C double prime. But what I have guaranteed now is that when I take I and I look at the component it belongs to, and now supposing this is the other component which has j, and I now merge this, then I moves from C to C prime, but C prime was at least as big as C, because C prime was the bigger component. So if C had some k elements, then C prime has more than k elements. So totally now the component of I has gone from k to something bigger than 2k, right? So the size of the component of I doubles every time it is labeled. Okay. So basically each time I relabel the component of I move it to a set which is twice as big as it was before, at least twice as big, could be even bigger. Now the other point to note is that when I do a merge, how many different elements change their component from the initial state. So initially, remember, I have 0 to n minus 1, okay, as components 0 to n minus 1. Now at some point I do a merge, so maybe I take I and j, so I take these and then they will both go say to j, right. So at this point I have touched I and j, so I have changed their component structure. In the case of one, I have changed the component name, and the other one I have changed it to be in a component which has new elements. Now the question is, after m such things, after m union operations, how many elements have had their component touched in this way? Either it has moved or something has come into it. Well, you can see that if I take 2 elements, then I touch 2, right. The next merge could, or next union could take 2 other elements and touch 2. So I could do 2 plus 2 plus 2, which is 2m, right. The first merge, first union merges these two, next union merges these two. But I can't do any more than that, I claim, because if I don't take 2 new elements, then I must be taking some set which was already been touched and one more element, right. So at most I can touch 2m elements, right. So this means that at most 2m elements have had their component updated since the beginning. But if at most 2m elements have had their components updated, the worst that can happen is that all of them have merged into a single component. I cannot have a larger component than that, right. So the largest component of any vertex in my set is at most 2 times n. So many of them will still have singletons, right. This is what we are saying, right. So after m union operations, the largest set in my partition cannot be bigger than 2m. So we have now these two facts. The fact is that each time I change the partition of I, it moves to a set which is twice as big. But it cannot grow beyond a certain size because across m operations it can only grow up to 2m. Right? So, combining this, we see that the size of a component will grow from 1 to 2 to 4 to 8, but it has to stop before 2m because it can't get beyond 2m because 2m is the largest set I could possibly have after m union operations. So, this means this doubling can happen at most log m times. That means if I pick a vertex and I examine how many times it changes its component, it can be at most log m times. Right? So, a single vertex cannot change its component more than log m times. So, this is what gives us now our better bound for union find, because it says that basically over m updates, first of all we know that at most 2m elements are relabeled and each of them is relabeled at most log m times, right. So, remember our relabeling operation is now optimal. I never look at a vertex to relabel unless I need to, because I am looking only at members of C. So, every time I decide whether to relabel a vertex or not, I am going to relabel it, right. I never look at a vertex and don't relabel it. So, if I only need to know how many relabel operations are there, because I never look at vertices or try to do anything with vertices in union when I am not relabeling them. But I know that A, there are at most 2m of them, because that is the limit of how many vertices ever get relabeled, and each one of them gets done at most log m times. So, if I add it up, it is like, again it is a similar analysis but in a more complicated setting. When we said that when you do breadth first search or depth first search using an adjacency list, then as we process all the vertices, we do the sum of the degrees, right. So, an individual vertex might add a lot of neighbors to the queue in breadth first search, but others will add less, and totally the number of neighbors I have to look at is going to be the sum of the degrees, and therefore it gets bounded by the total number of edges. Similarly, here we are saying that the total number of operations of relabeling across all the m union operations is going to be m times log m, because 2m order of m times log m, let us say, because 2m vertices are going to get, or elements are going to have the neighbors change, and no element is going to be touched more than log m times, right. So, therefore, over m union operations, I will not do more than m times log m work in terms of changing component numbers, right. So, this is where we have saved, right. So, instead of going to m times n, we have come to m times log m. So, this means that if I have, since I am assuming that there are m of them, right, I can take m times log m, right, and I can say what is the cost of one of them, I divide by m. So, on an average, in a sense, each of them is only taking logarithmic time, right. So, it is not that any one of them is actually taking logarithmic time for sure, because I know that sometimes I have to merge a large component, but then many of the times I will be merging very small components, and if I add it up, so this is again this notion that we saw with as I said with BFS and DFS when we were dealing with adjacency lists, that we count the cost across the entire operation and say the total sum of the operation can only be so much, even though individual operations can be more, right. So, this is this notion of amortized, what you gain in one place you will lose in another place, but overall it will all work out, right. So, the amortized complexity of one union operation is log m, even though individual union operations could be more expensive. Totally m log m is the cost of m such operations. So, how does this affect Kruskal's algorithm? So, this is where we started looking at these operations, because this was the context in which we needed it, right. So, remember that in Kruskal's algorithm we start by sorting the edges. So, we take the edges, there are m of them, and we sort them in ascending order. After this, we have to start this business of creating the tree. So, we have to keep track of these components. So, we first do a make union find, which will take order n time for our n vertices, right. So, this is going to be order n time. Now, when I check whether a vertex needs to be added or not, I need to look up the component name of the two endpoints, but this is order 1 time because I just have to look up my component added. And now this is the step which was bothering us, right. So, earlier this was taking order n time when we did it naively, but now we know in this amortized sense this is going to take log m time. So, how many union operations are we going to actually perform? Well, because we are constructing a spanning tree on n vertices, and a spanning tree on n vertices, remember, will have n minus 1 edges exactly. We are going to do exactly n minus 1 union operations. So, we can think of it as order n union operations. So we saw earlier that if we do order m, if we do m operations, it's m log m. So here it is n operations, so it's n log n, right? So the total cost of all these union operations across each addition that we actually perform. Remember that if find u turns out to be find v, we just throw away the edge, so we don't have to do anything. So only when find u is not equal to find v, when they are in two different components, we have to do a merge. But now what we are saying is that this merge, right, will actually happen overall. The overall cost of these merges, there will be n of them, will be n log n, right. So this is the amortized cost overall of the union operations. So now if we go back to the first step, this is another expensive step. This takes m log m time using an optimal sorting algorithm. So we have seen that, you know, things like merge sort, for instance, are m log m, and a naive algorithm like insertion sort or selection sort could be m squared. But you can't beat m log m, we said, without giving a proof saying that that is a lower bound. So we need to spend m log m time to sort. So we need m log m time to sort and n log n time to do the unions. Now this is kind of a bit awkward to have log m here and log n there, right. But notice that m is at most n squared, right. So if I take logs on both sides, I will say log m is less than or equal to 2 of log n, right. So this is how logs work, right. So log of m is actually big O log of n, it is some constant times log of n. So I can say that m log m is the same as m log n, right. So now I have the same thing on both sides now I am in good shape. I have n log n and I have m log n. So I can now combine them and claim that the overall time of Kruskal's algorithm is m plus n times log n, right. So remember that this really is the size of g, right. So we are really saying that in terms of the size of g, it is n log n. I mean, if you think of capital N as the size of g, it is within capital N log n, and this is probably the best that one could hope to do, given that you have to do sorting and all that, right. So this is how this union find algorithm actually helps us bring Kruskal's algorithm down from n squared to something like n log n, right. So what we have seen is that if we use this two-way mapping, right. So component is the obvious thing, it tells us given an element which component it belongs to. But if we keep the reverse mapping, given a component which are the elements which belong to it, then we can relabel these components efficiently by also keeping track of the size. Always merge a smaller component into a bigger component. And if we just follow this rule of merging smaller components into bigger components and keep track of the components using this member array, right, then, or member dictionary, then we can guarantee that across m operations, the amortized complexity of each union operation is log m. So m log m is the total cost of all the unions. Find remains constant time because it's just looking up a dictionary value, and make union find remains linear time because I have to actually reset the component to a singleton for everybody. So this is a very direct and easy way of doing union find. There is a slightly more complicated way where instead of keeping these members of K as a list of vertices, you can keep it as a tree, right. And if you keep it as a tree, then it turns out that the union operation becomes very simple, right. So basically I will have members of I, so this will be some tree, and I will have members of say j, and this will be some other tree. And the rule is that if you belong to the same tree or in the same component, so the union operation will just either connect this tree that way or connect this tree this way. So it will just take the root of one tree and put it as a child of the root of the other tree. So the union operation is very simple, I just stick one tree under the other tree. But now find means I am sitting here and I must go up to the root vertex will tell me which component I am in. So we have to be careful that these components, these trees don't become very tall. And there is a clever way of keeping them not only from growing very tall, but actually flattening them, right. There is something called path compression that you can do. And if you do this path compression, eventually your tree will look like this, where everything, so if I have a component and then I have all the other vertices which belong to the component will be only one step below. So it will only take me one lookup in order to tell you what component is. So it will have an amortized complexity of almost constant time. So both union and find become, so union is constant and find is almost constant. So this is really the ultimate implementation that you could have for this, where you can keep track of this and then each operation is a unit cost. Okay, but we will not go into that now, but you can look it up. It's a very interesting optimization of this union find data structure.